Hello all, welcome to Unacademy. Crack GATE ESE with India's largest platform, online learning platform. Okay, so get subscription for the plus subscription and access unlimited live and recorded courses from the India's best educators. So get subscription. Now before going to start this, let me introduce myself. Myself Dhanashree Mam. I completed my MSc in Mathematics from Mumbai University. I am also having 13 plus years of teaching experience and mentored more than 10,000 plus students for the engineering. Now, here how to install the Unacademy's Learning app and how to get the plus subscription. Here see. Now, what you will get in a plus subscription and iconic subscription. Okay, so daily live classes you will get, daily live test series and quizzes here you will get. Now chat with your educators in a daily live classes, engage in discussion, ask your doubts and answer polls all while the class is going on. Now evaluate your preparation with your regular mock test and quizzes and get detailed analysis on your performance. And structured courses, all our courses are structured in the line with your exam syllabus to help you the best prepare for it. Now unlimited access is also there. For the one subscription gets you will access to all our live and recorded courses to watch from the comfort of any of your device. Okay. Now the iconic subscription, here you will get the iconic subscription plan. In that personal coach you will get, so that you can ask your doubt one on one, that is get one on one guidance from the top exam experts as your personal coach, and align your preparation strategy and learning resources. Now mains and Q and a practice is there, question answer practice is there, and strengthen your mains answers writing through the regular practice with the evaluation and personalized feedback. Now next is study tracker. Participate in study tracker, plan and study booster workshops. Evaluate your progress in by weekly reviews with the personal coach. Now all benefits of plus, so you will get here in an iconic subscription. It means all the benefits, that is live classes, recorded classes, you will get question answers, personalized. Here in the main important thing in iconic subscription, you will get your personal coach. Okay. No. The plus subscription, daily live classes are there, all the live test series and quizzes are there, structured courses are there, unlimited access is here. When subscription gets to access all our live and recorded courses to watch from the comfort of any of your devices. Okay. Now, now here learn with the top educators, that is here Amar Tiwari sir, Ankit Goyal sir, Sanchit Jain sir, Jaspal Singh sir. Here all the top educators are here to educate you, and you will get the one-to-one guidance for your preparation. Now here also some top educators from Unacademy. Now these are also some top educators from Unacademy. And the courses are available for GATE and ESE batches and year-long courses. That is, there are 38 courses here. Mechanical engineering, there are 24 courses. Electrical engineering, there are 18 courses. Here, electrical engineering courses, 10 courses. CS and IT, there are many more courses are available for your GATE and ESE for the all branches of engineering. Now here, get select plus subscription, you will get the India's best educators, interactive live classes, structured courses and PDFs, and live test and quizzes. In Iconic, you will get all of this. You will get all these facilities in Iconic, and plus the other facilities, that is live personal coach you will get, personalized test analysis, study planner you will get, and preparation study material as preparatory study material also you will get in the Iconic subscription. So this is your plus point of getting a Iconic subscription. You will get all the facilities of plus subscription, as well as these are the main important facilities for the Iconic subscription. Now plus plan, you will get the plus plan here. Details are given here. The plus plan is here given for the 1 month the fee structure is given here for 3 months, for 6 months, for 12 months. If you're going for to prepare for the 12 months, it is more easy to prepare, do your study in a well manner. And for the 12 months, it's here also. And if you want a 10% discount on your any one of these three for the plus plan, you can use my promo code here DSP to get the 10% discount on your subscription fees. The same is here. You can use my promo code, that is DSP, to get the 10% discount on your subscription fees. Okay, so for the iconic plan also you will get the subscription. For the 12 months iconic plan is 50,250, and for the 12 months here GATE ESE subscription for the iconic plan is here, after getting the 10% discount on it, you will get total inclusive of all taxes, that is 45,225. See the huge difference is there. You will get 5% discount, or sorry, 10% discount on your subscription fees if you use my promo code, that is DSP. Okay. Now, here evolve your batches for the new batches will be going to start for the GATE ESE exam for the new branch, that is in the civil engineering. So here you will get a new batch alert for the batch C. Now batch A, B are already started. For batch C is evolve for the GATE 2022. Here the top educators are, you can see the top educators here of Unacademy. That batch will be start from the 25th January 2021. Okay, so you can use, again I will tell you here, to get the 10% discount on your subscription fees, you can use my promo code, that is DSP. Now your new batch for C, a second for GATE 2023, that is for GATE 2022, and here is for the GATE 2023 is also there, which is starting from 25th of Jan 2021. So for all uh, your subscription fees, you can get a 10% discount if you use my promo code DSP. Okay. Now here again the third batch A, your new batch alert for the GATE 2022 for the chemical engineering. You will get it here. Ankur Bansal sir, Shailendra Kumar sir, everybody is here, the top educators of Unacademy. So that batch also starts from 25th of January, and for to get the 10% discount on your subscription fees, you can use my promo code DSP. Now, for again the batch A will start for the chemical engineering. Here that batch again start from the 25th of January. Okay. Now, here a second batch for GATE 2023 is again starting for the mechanical engineering. That is Praveen Kulkarni sir here, GS Gill sir. So all the top educators are available here. He is ready with uh, a strong material to guide you and to educate you. So please enroll your names to get the subscription plan, either plus subscription or iconic subscription, and to get the 10% discount on your subscription fees, you can use my promo code DSP. Okay, so that's it. Now we will start our the next lecture on discrete mathematics. Okay, that is your 17th lecture. So I will cover up all the topics from the discrete mathematics which help you to for the semester exam as well as for the GATE exam. Okay, so discrete mathematics, your 17th lecture, which, and again lecture number 4 on Eulerian on graph theory. Okay, this is the lecture number 4 on graph theory. In previous 3 lectures I have covered most of the part, that is definitions of a graph, types of a graph, and main important thing, that is shortest path algorithm. Yesterday we have seen the shortest path algorithm, Disgust-Strass algorithm, and in this lecture we will see the Eulerian path and Eulerian circuit, Hamiltonian path, Hamiltonian circuit, and nearest neighborhood method. How to find out the Hamiltonian circuit by using nearest neighborhood method. Okay, so let's start. Now here is Eulerian path. So what is the definition of Eulerian path? A path is known as a Eulerian path if every edge of the graph G appears exactly once in the path. Okay, every edge of the graph G appears exactly once in the path. That is your Eulerian path. Now Eulerian circuit. Now we know that in the yesterday's lecture what you mean by circuit. If the starting and ending vertex is same, then that circuit is called as, that path is called as circuit. Okay, now Eulerian circuit, obviously the circuit which contains every edge of the graph exactly once is called as an Eulerian circuit. Every edge of the graph which appears exactly once is called as Eulerian circuit. Okay. Now Eulerian graph. A graph which has an Eulerian circuit is known as Eulerian graph. Now let's see the examples of these graphs where the Eulerian circuits and Eulerian graph is there. Okay. So let's start now. We'll see one examples on this Eulerian circuit. First, suppose this is your graph. Here is Eulerian graph. Suppose here A, B, C, D, E. Right? Here is A, B, C, D, and so this is your graph. Just simple graph, you can say F. Okay. Now, is this graph contains a Eulerian circuit? Okay, forget about this. A graph which has an Eulerian circuit is known as Eulerian graph. If it is having a Eulerian circuit, okay, suppose A to B, B to E, E to D, E, D to C, C to A is a, so A, B, E, D, it is a path we can say here, alternating sequences, vertices and edges. So E1, E2, E3, E4, E5. So A, E1, B, E2, E, E3, D, E4, C, E5 and A. So starting and ending vertex is same. Here starting and ending vertex is same, therefore this is a Eulerian circuit. Why it possesses an Eulerian circuit? Because no edge is repeated in this graph. So this is your Eulerian circuit, and if a graph contains a Eulerian circuit, then it is called as Eulerian graph. Okay, now see, this graph contains a Eulerian circuit. Now if I take this vertex again, suppose if I now the same graph, okay, forget about this, just keep as it is. Here E2. Okay, I'm drawing the another graph here. This is an example which contains Eulerian circuit as well as Eulerian path. This is also Eulerian path, and Eulerian path which contains no edge is repeated, that is your Eulerian path. An Eulerian circuit also, and a circuit contain graph contains a Eulerian circuit, then it is a Eulerian graph. Okay, now Eulerian I will give you an example where it contains a Eulerian path but does not contain a Eulerian circuit. Okay, if I draw the graph like this, now this is your graph. Here is A, B, C, D, E, F. Right, now this is your Eulerian circuit, sorry, this is your graph in which it contains a Eulerian path. It means every edge appears exactly once. Okay, so you can give you a path A, F, B, A, F, E or anything. So A, F, E, D, C, F. Okay, so you can see that A, B, C, D, E, F, C, right? Every edge appears. A, E1, E2, E3, E4, E5, E6. This is your graph, suppose G2. Okay, the first one is graph G1. G1 has Eulerian circuit. You can say G1 has Eulerian circuit. Okay, now next is G2. So for G2, so A, E1, B, E2, C, E3, D, E4, E, E5, F, E6, E4. So every vertex is covered. Yes, from A, every edge is covered. A, E1, E2, right? A E1, E2. So if I go like this, so every vertex is covered. The graph contains a Eulerian path, but it need not have a Eulerian circuit. Okay, F E4 you can take, E6, E7, right? So it will have a Eulerian path but not Eulerian circuit because we cannot come to the again end point. So this will have a Eulerian. E4 is repeated two times, no? 1, E2, E3, E4, E5, E6, E7. Okay, E6 is here. So we'll go like this. So this is your Eulerian path. Now this graph will contain G2 contains Eulerian path. G2 contains Eulerian path, but not Eulerian circuit. Clear? Because every edge appears exactly once, and if you want to go for the vertex A again, then that vertex will be repeated. That edge will be repeated. Okay, so this will contains a Eulerian path, but not Eulerian circuit. Yeah. So here is A E1 B E2 C C E7. Can take this path. C E7 F E6 F E5 E E4 D. Now every edge appears in this path. So G2 contains no matter if the vertex is repeated in the Eulerian path. So G2 contains Eulerian path but not Eulerian circuit. Okay, an example. Now, the very important thing is that an undirected graph possesses an Eulerian circuit. This is very simple criteria. An undirected graph possesses an Eulerian path if and only if it is connected and has either 0 or 2 vertices of odd degree. If and only if it is connected and having either 0 or 2 vertices of odd degree. Okay, so you will get it here. The two vertices of odd degree. An undirected graph has an Eulerian path if and only if it is connected and either vertices are having odd degree. Okay, two vertices of having odd degree. Now let's see here how it is. Okay. Now, an undirected graph possesses an Eulerian path if and only if it connected and has either 0 or 2 vertices of odd degree. Now, if you see this example, in this example, the two vertices are having odd degree. Now, see. So therefore, it is having a Eulerian path, right? Exactly two vertices of odd degree or zero vertices of odd degree. Now, if you see here, zero vertices of zero vertices of odd degree. No vertex is having odd degree, right? So this will connect. The graph is connected, and either 0 or 2 vertices of odd degree are present. Then definitely that graph will possesses an Eulerian path. Now theorem 2. An undirected graph possesses an Eulerian circuit if and only if it is connected and its vertices are all of even degree. Okay, possesses an Eulerian circuit if and only if it is connected and its all vertices are of even degree. So this is an example. All the vertices are of even degree. So every vertex is having degree 2, right? All the vertices are having degree 2. So therefore it possesses an Eulerian circuit. Now if you see this, now all vertices are not having a degrees even. So therefore, this graph will not contain a Eulerian circuit. So, very simple criteria to remember whether the graph contains Eulerian circuit or not. Okay. Now, suppose here An undirected graph possesses an Eulerian circuit if and only if it is connected and vertices are of all even degree. If all the vertices of the given graph G has even degree, then definitely that graph will possess an Eulerian circuit. Okay. A directed graph possesses an Eulerian circuit if and only if it is connected and the incoming degree of every vertex is equal to the outgoing degree of every vertex. In the directed graph, the incoming degree and outgoing degree is same, then we say that that graph will possess an Eulerian circuit. Okay. Now, a directed graph possesses an Eulerian path if and only if it is connected and the incoming degree of every vertex is equal to the outgoing degree with the possible expectation of two vertices. For these two vertices, the incoming degree of one is 1 more than the outgoing degree of the outgoing degree and the incoming degree of other is 1 less than the outgoing degree. It means at least two vertices possesses a degree 2 sorry two at least 0 or 2 vertices possesses a odd degree, then that will have a Eulerian path. Okay, now we will see one example where draw a graph which contains an Eulerian circuit. Now it is easy to draw the graph which contains an Eulerian circuit. Now we know that the criteria which graph will contains an Eulerian circuit, that graph will contains a Eulerian circuit if degree of every vertex is even. Okay, so that we can draw a graph in a such a way that degree of every vertex is even. So you can draw the graph here. Degree of every vertex is even. Okay. Suppose this is our graph. Here we can see there is A, B, D, E, F. Now if you see the degree of every vertex is here even. Degree of every vertex is even. Here is degree degree of this vertex is 4, 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 degree of this vertex is 4 and degree of this vertex is also 4. So every vertex is having even degree. So definitely this graph will possess an Eulerian circuit. No need to other criteria. No need to check the other criteria. Only check the degree of the vertices. If it is even, then definitely that graph will possess an Eulerian circuit. Okay. Now next, draw a graph which contains an Eulerian path but does not contain an Eulerian circuit. So what we have to do? At least we have to find out the two vertices who is having degree odd. Okay, and there exist at least two vertices of either zero vertices of odd degree or two vertices of odd degree. So then definitely that graph will possess an Eulerian path but not contain Eulerian circuit. Okay, so we can draw a graph in a such a way that the same graph if we take and we'll manage the degree of this vertex. Okay. 4, 5, 4, 1, 2. There are at least two vertices. Now see degree of vertex is here 4. Degree of vertex C is 3. degree of degree of vertex C is 4 and degree of vertex B is 3, degree of vertex A is 5 and degree of vertex F is again 1, 2, 3. Degree of this vertex is again 3. 1, 2, 3, 4, 5, 6. So here are two vertices B and F having a degree here 3. So there are exactly two vertices of odd degree. So definitely this graph will possesses an Eulerian path but does not contain an Eulerian circuit. I hope you are getting the criteria clear here, which graph will contain an Eulerian path and Eulerian circuit. If the graph is having a vertex of every vertex of degree even, then definitely that graph will possesses an Eulerian circuit. And if that graph is not having at least two vertices are having odd degree, then definitely that graph will possesses an Eulerian path. Okay, we'll go further. Now find under what conditions KMN, the complete bipartite graph, will have an Eulerian circuit. And find under what conditions KMN, the complete bipartite graph, will have an Eulerian circuit. So to get the Eulerian circuit, we have to impose a conditions on M and N. Okay, so in a complete graph KMN, we can say that here the following cases. First of all, we will see the complete graph of KMN. It means first case. Suppose M is equal to N. If both M and N are equal, then what will happen? If both M and N equal and are even, okay, and both M and N are even, then what will happen? The degree of every vertex is even. So by that criteria, the degree of each vertex is even. Degree of each vertex is even, and hence the graph KMN will contain Eulerian circuit. Why? Because degree of every vertex is even. By default it is contain an Eulerian circuit. Now you can see that KMN vertices K22, suppose two graphs. So definitely when for example if I take the K22 graph where 2 is even, complete bipartite graph, vertex set V1 contains two vertices, right? This K22 graph, definitely it will have a Eulerian circuit, right? K44 complete bipartite graph, both M and N are even, then definitely it will have an Eulerian circuit. Now we'll see the next case, case 2. Suppose F and M and both are odd. Okay. If M is equal to N and M and N both are odd, then degree of each vertex is odd, right? Then degree of each vertex is odd. Okay. If M is equal to N and M and N both are odd, then degree of each vertex is odd. Okay, so definitely this will not contain an Eulerian circuit, right? Then it will not contain an Eulerian circuit. Now when we will have the Eulerian circuit, if both the circuit is having degree of every vertex is even, then only that circuit will have a Eulerian circuit. Now here M and N, bipartite graph, complete bipartite graph, we are considering the cases in which case the complete bipartite graph will have an Eulerian circuit. In the case M is equal to N, the graph will have Eulerian circuit. But if M is equal to N and M and N both are odd, then degree of each vertex is odd, then definitely this graph will not have an Eulerian circuit, because degree of every vertex is odd. Graph will not have Eulerian circuit, right? Graph will not have Eulerian circuit because it is the degree of every vertex is here odd. Okay, so definitely it will not have a Eulerian circuit. Now what will, suppose this is K33. If we take the K33 graph, complete bipartite graph on 3 vertices. Okay. So complete bipartite graph, it means there is an edge from every vertex to the vertex set V1 to V2. Right? Here degree of every vertex is 3, so which is odd. So definitely this graph will not have a Eulerian circuit. Now the case C we'll consider. If M is not equal to M, case 3. In case 1, M is equal to N and both are even, then it will have Eulerian circuit. Case 2, M is equal to N and both are M and N are odd, then it will not have a Eulerian circuit. Case 3, if M is not equal to N and M and N both are even, and M and N both are even, then what we'll have? Okay, then the graph has Eulerian circuit because degree of every vertex is even, right? Now, then graph have Eulerian circuit. Then graph have Eulerian circuit as degree of every vertex is even. As degree of every vertex is even. Okay, so it will have a Eulerian circuit as degree of every vertex is even, right? So suppose this is, if I take M is not equal to N, so K24, take the complete graph on 2 vertices, so K24. Okay. Okay, 2, 4. So this is the vertex set V1 contain 2 vertices. Now if you see, the degree of every vertex is even. Here degree of every vertex is 4. Here degree of every vertex is 2. So definitely this graph will possesses an Eulerian circuit. Okay. If M is not equal to N and both are even. Now the next case. Case 4. Okay. So what is the case? M is not equal to N. Okay. Either, now we'll consider both the cases here. Either M is odd or N is odd. Either M is odd or N is odd, or both are odd. Or both are odd. Then definitely the degree of every vertex which have not possesses an Eulerian circuit. Then graph will not contain Eulerian circuit. Yes, we already seen if M and N both are odd and are not equal. So we can see that here. Suppose this is a graph K35. Suppose we take 5. K35. If you see this, then definitely degree of every vertex is odd. So obviously this graph will not contain an Eulerian circuit. See, this graph will not contain an Eulerian circuit. Right? Graph will not contain an Eulerian circuit. K35. Either M is odd or N is odd. Here or both of are odd. So we can see either M odd or N odd. So if you see here K23. Suppose one more example. Either one of them is odd. So here N is odd. If you see here, degree of every vertex is, here degree of every vertex is even. 3 vertices are having degree 2, which is even, and 2 vertices are having degree 3, which is odd. So definitely this graph K23 also will not contain an Eulerian circuit. So under which condition the K complete bipartite graph is a having Eulerian circuit. If M and N both are even, then only the graph will have Eulerian circuit. Okay. Or third case, if M is not equal to uh, third case, M and N both are even, then only it will have Eulerian circuit. Okay. Now, next is, now I think you are totally clear about the Eulerian circuit and Eulerian path. Okay. Now here we will see the Hamiltonian path and Hamiltonian circuit. In the Eulerian circuit and Eulerian path, only what we will take? Only edges will take. If edges are not repeated, then we'll have a, every edge of the graph will appear exactly once, then that graph will have a Eulerian path or Eulerian circuit. Starting and ending vertex is same. Then, now here Hamiltonian. Now Hamiltonian graph and Hamiltonian path is regarding with the vertex. In this, edge can be repeated, but vertex is not repeated. In the Eulerian, edge cannot be repeated, but vertex can be repeated. Okay. Now, a problem is similar to the determination of an Eulerian path or Eulerian circuit. It is to determine a path or a circuit that passes through each vertex in a graph once and only once. It means every vertex of the graph appears exactly once in the Hamiltonian path and Hamiltonian circuit. We define a Hamiltonian path or circuit to be a path or circuit that passes through each of the vertices in a graph exactly once. Okay. Sir William Hamilton invented the game all around the world, in which the player is asked to determine the route along the dodecahedron will the pass through each angular point once and only once. Okay. Now here Hamiltonian path. Okay. What do you mean by Hamiltonian path? A path in a connected graph G is a Hamiltonian path if it contains every vertex of G exactly once. If it contains every vertex of G exactly once, then the graph will have a Hamiltonian path. Hamiltonian circuit. A circuit in a connected graph G is a Hamiltonian circuit if it contains every vertex of G exactly once except the first and the last vertex. Okay. Hamiltonian circuit. A circuit in a graph G is a Hamiltonian circuit if it contains every vertex of G exactly one except the first and the last vertex. Okay, exactly similar way in the Eulerian graph, no edge is repeated. In the Hamiltonian graph, no vertex is repeated. Okay. Now, there is suppose here one example I will tell you where it contains an Hamiltonian path. A very interesting diagram. Dodecahedron. There is 3 starting from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Right? There is there 16, 17, 18, 19, 20. Now, you can draw this as yeah. Now, such Hamilton circuit, you can see that. So this one Hamilton circuit in which every vertex appears exactly once. Okay, so we can see that here. One such Hamiltonian circuit is, you go like this: 2, see, 2, 3, 10, 11, 12, 4, 5, 1, 6, 7, 17, 16, 15, 14, 13, 20, 19, 18, 9, 8, 2. Now see, every vertex appears exactly once. So this is your Hamiltonian circuit. Okay, Hamiltonian circuit. Every vertex of the graph appears exactly once except the first and last vertex. Okay, so this is your Hamiltonian circuit. So you can see here 2, 3, 10, 11, 12, then 4, 5, 14, 15, 16, 5, 4, 5, 1. Now next is 5, 1, 6, 7, 17, then 16, then 15, 14, 13, 20, 19, 18, 9, 8, 2 again. Okay, so in this way we can find out the Hamiltonian circuit in which no vertex is repeated except first and last vertex. As like the criteria we have seen for the Eulerian graph and circuit, exactly similar way here is a criteria to find out the whether this graph will have Hamiltonian circuit or not. Okay, so first criteria or theorem, let G be a simple connected graph on the n vertices if sum of the degree for each pair of vertices in G is n minus 1 or large, then there exists a Hamiltonian path. मतलब अगर यहाँ पे आपका जो ग्राफ है वो n is equal to अगर 5 vertices के ऊपर है तो degree of every vertex must be 5 minus 1, that is 4, then there exists a Hamiltonian path. Okay, now so theorem 2. If G be a G be a graph with vertex set V and edge set E is a simple connected graph on the vertices, and if degree of each vertex V is greater than or equal to n by 2, then G will contain a Hamiltonian circuit. Okay, let G be a graph with vertices V and edge set E is a simple connected graph on vertices, and if the degree of each vertex and the degree of each vertex V is greater than or equal to n by 2, then the graph G will contain a Hamiltonian circuit. Okay, now let's see one example here. Suppose this is your graph. Okay, here is A, B, C, D, E. Okay, so this is the graph. Now these are the 5 vertices. Okay. Now for this graph, the total number of vertices n is equal to 5, and the degree sum of every pair of vertices is here 4. So then hence it is existent Hamiltonian path, right? Degree sum of every vertices is n minus 1. So n minus 1 is equal to 4. So if you take any pair of vertices, suppose if you take pair A and B, so degree sum of these two vertices A and B is 4. Degree sum of D greater than or equal to 4. Degree sum is greater than or equal to 4. So 4 is there. So if you take C and E, so degree sum is 6, which is greater than 4. Degree sum of D and C, that is 4 plus 2, 6, which is greater than 4. Degree sum of B and E, which is equal to 4. Degree sum of A and D is equal to 4. So definitely this graph will have Hamiltonian path, okay, in which every vertex appears exactly once. Okay, so we can see that A, B, C, E, D is the Hamiltonian path. So Hamiltonian path is A, B, C, E, D. Right? There exists a Hamiltonian path as degree sum of each pair of vertices is greater than or equal to n minus 1. Okay. Now, thus, so this condition is necessary but not sufficient. If I'm giving you one more example, it means Hamiltonian path आने के लिए this condition is necessary but not sufficient. मतलब अगर यही है तो ये Hamiltonian path होगा, ऐसे नहीं है. Now you can see this. This is a graph. 1, 2, 3, 4, 5, 6. Okay, there are 6 vertices. And if you see the degree sum of pairwise degree sum and n is equal to 6, so n minus 1 is equal to 5. But degree sum of these vertices is 1 plus degree sum of 1 and 2 is 4, right? But 4 is not greater than 5. So still this graph is having a Hamiltonian circuit. See, 1, 2, 3, 4, 5, 6. This is your Hamiltonian circuit. So it means to possess, the graph possesses Hamiltonian path. It means that it is not necessarily, that condition is necessary but not sufficient. This is necessary condition but not sufficient. मतलब अगर यहाँ पे डिग्री सम अगर ग्रेटर देन और इक्वल टू n माइनस 1 नहीं होगी तो ग्राफ में एग्जिस्ट नहीं है हैमिल्टोनियन पाथ, ऐसे नहीं बोल सकते, राइट? दिस इज एन एग्जांपल that this is a Hamiltonian in which degree of every pairwise degree sum is not greater than or equal to 5, but still the graph will have a Hamiltonian path. Okay, and the Hamiltonian path is 1, 2, 3. Hamiltonian path is 1, 2, 3, 4, 5, 6, right? So this is your Hamiltonian path. And if you observe, this graph will also possesses a Hamiltonian circuit. So 1, 2, 3, 4, 5, 6, 1. Okay, starting and ending vertex is same. Now, the criteria for the Hamiltonian circuit. Let G is equal to V is a simple connected graph on a vertices on n vertices, and if the degree of each vertex is V is greater than or equal to n by 2, then G will contain a Hamiltonian circuit. The degree of every vertex is greater than or equal to n by 2. So n is equal to, here you can see, here n is equal to 6. So degree of every vertex greater than or equal to n by 2, that is 6 by 2, it means 3. But which is not possible, degree of every vertex is 2. Again, this condition of having a Hamiltonian circuit is necessary but not sufficient. Okay, if the graph is contain every vertex of degree n by 2 greater than or equal to n by 2, degree sum is greater than or equal to n by 2, then definitely that graph will have a Hamiltonian circuit. Okay. Now this is an example where this will have a Hamiltonian circuit, but degree vertex is degree of the vertex, each vertex is 2, right? Not greater than or equal to n by 2. So degree of this vertex is 2, not greater than or equal to n by 2, right? Now, let G be the next. We'll see more example. Yes. Hamiltonian circuit exists in a complete graph, complete bipartite graph. Justify your answer. Hamiltonian circuit exists in complete bipartite graph, okay? Justify your answer. Justify your answer. As we know that Hamiltonian circuit exists in a complete bipartite graph for which m is equal to n, and Hamiltonian circuit does not exist in a complete bipartite graph Kmn for m is not equal to n. Okay, now consider Kmn is equal to Mn. So vertex set of V1 and V2 partitioned of vertex set of Kmn. Now Hamiltonian circuit exists, we can write here, Hamiltonian circuit exists in complete bipartite graph, Kmn for which m is equal to n, and Hamiltonian circuit does not exist in complete bipartite graph, Kmn for which m is not equal to n. Now consider, here we can say that consider Kmn such that the vertices V1 and V2 be the partition of the vertex set Kmn, and vertex set of V1 contains m, vertex set of V2 contains n. Then where m is less than n, then the graph Kmn minus V1 is a null graph on the vertices, and hence it is a disconnected graph with n components. So therefore the number of components of Kmn minus V1 is less than or equal to mod of V1, that is m. So definitely, which is contradiction to m is less than n. So hence by theorem we'll get Kmn does not contain a Hamiltonian circuit for m is not equal to n. Okay. Now, next point is nearest neighborhood method. Okay, in this method we start the Hamiltonian circuit with any arbitrary vertex. Okay, in this method we'll start a Hamiltonian circuit with any arbitrary vertex and find the vertex which is nearest to it. Continuing in this way and coming back to the starting vertex by traveling through all the vertices exactly once, we get the Hamiltonian circuit. Now the process is described as follows. First step, start with any arbitrary vertex and find the vertex that is closest to the starting vertex to form an initial path of one edge. Okay, we are starting with initial path with one edge. Now construct this path by selecting different vertices as described in step 2. So let x denote the latest vertex and was added to the path. Among all the vertices that are not in the path, pick up one that is closest to x and add to the path an edge connecting x and this vertex. Repeat this process until all the vertices in the graph G are included in the path. Okay. For a circuit, by adding the edge connecting the starting vertex and the last vertex added. Okay. Now, for the following figure, solve the following option. First one, use nearest neighborhood method to find out the Hamiltonian circuit for the graph in the following figure. Now repeat this process part A starting with vertex D instead and determine the minimum Hamiltonian circuit for the graph in the following figure. So we will draw the figure first. That is A, E, C. That is weight 5, 4, 2. D, there is 2. There is E, 5. 2D, weight 3. D2E, D2E, weight again 3. D2E, weight 2. Here A to D, 5. Here A to E, weight 8. Right? So for the following figure, solve the following options. Use nearest neighborhood method to find out the Hamiltonian circuit for the graph in the following figure. Okay. Now here is given that using repeat the part A for the vertex. So here starting with the vertex A. Now initially we will start with vertex A here. Okay. So find out the Hamiltonian circuit by using nearest neighborhood method. So the procedure is to find out the nearest neighborhood method with any arbitrary vertex. So with any arbitrary vertex, I will start with A. Now after A, choose the minimum weight to reaching to the next vertex. So the minimum weight from A to the remaining vertices is 4. So I can go for A to C. Okay. So the initial path you will get here. Initial path, first step, start with vertex A. Start with vertex A. There are 4 adjacent vertices. There are 4 adjacent vertices B, C, D and E. The closest vertex is C, as length of A and C is 4, which is minimum. For first reference I am writing everything which is minimum. Okay. So initial path you will get, initial path is equal to AC 4, that is B, D, the initial path is 4. Okay. Now there are 3 vertices adjacent to C. You can see there are 3 vertices remaining except A. Adjacent to C, that is B, D and E, and which one is the minimum? B. We can take the path. Second step, so path you will get here B, path A, C to B. Okay. Let the go to A, B. All the vertices we have to draw. Now for B, the remaining vertices which are adjacent to B are except C, the path with the vertices which are already present in this path P. So except this, which one is the smallest path from B to the remaining vertices? So 2 is the minimum weight. Now the vertices are joining to E and D only because A is already covered in the path. So B to D is the minimum distance, that is 2. So we will go from step 3. Path A is equal to A, C, B, D. Right? So you will get the path like this: A, C, B, D. Right? There is D. 2, 2. Okay. There is E. Now third one, fourth step. So path you will get is fourth step. Now which one is adjacent to D? Is adjacent to how many vertices? Now to the vertex A, which is already covered, to the vertex C, which is already covered. Now to the vertex B, which is already covered. Now which is remaining? Only E, and the A here weight of that is 2. Sorry, yeah. There is weight is D to E is 2. So we can take it here, path A, C, B, D, E. Okay. So here is 2. A, C, 4, D, 2, D, 2. And here is E, right? Now, if you observe, all the vertices are covered, but we have to reach again to find out the Hamiltonian circuit. We have to reach again the starting vertex. So, if you see which path I have to take again to take the starting vertex, yes, there is no option. We have to go by E to A. So, E to A is the H. So, fifth proper path, okay, A, C, B, D, E, A. Right? We will get the Hamiltonian circuit like this. With the minimum weight, you have to find out. A, B, here is 4. Sorry. 4, 2, 2, 2. The minimum weight is 4 plus, and this is 8. 8 plus 4, 12. 12 plus 6, that is 18. So you will get the minimum weight Hamiltonian circuit with starting with vertex A is minimum weight is 18. So this is your, now the repeat, we have to repeat the same process starting with the vertex D instead. मतलब A की जगह पे हमें D vertex लेके start करना है. Okay, so start with D. Now what are the vertices adjacent to this? So you can choose. Now here are two vertices having same weight, right? B and E. So you can choose any one of them. So I'm choosing it here E. Okay, starting with vertex step 2. Starting with vertex 2. Vertex D, second vertex instead of A. Okay, so I'm again drawing the same graph here. So if you see here, so starting with D, so you get there is A, B, C, D, E. So the initial path is this. So path is equal to D to E, right? This is. Now secondly, without writing anything, I'm directly write down here. First step, second step. Now vertex E is adjacent to many vertices. So choose the minimum. So vertex E is adjacent to vertex B. See here. E is adjacent to vertex B, C and A. With minimum of them is B. Right? So you will get the path here. Minimum of that vertex is again B. So you will reach from E to B. Right? E, A, B, C, D, E. Here D to B. Here weight 2, D to B is 3. Right? So D to E is 2, D to B. So path you will get D, E, B. Okay. Now from B. So B is adjacent to how many vertices? C, A, D and E. But D and E already covered. So only remaining is C and A. With minimum is 3. Minimum weight is here. C is, we can reach from B to C with minimum weight 2. So I will take that path. Okay, so third step. At third step, path here D, E, B, C. Right? D, E to E, E, B, E to B, B to C. Right? Here with weight 2, 3 and 2. Now next step is fourth one. Now vertex C is adjacent to many vertices here. You can see C is adjacent to B, E, D, but B, E, D and E already covered. So only remaining is A. So we will go to the A, right? So here path is D, E, B, C, A. B, C, B, C. Okay. So we can go for from C to A. Minimum weight 4. Now if you observe, all the vertices are covered, but again we have to come back to the vertex D. So there is only one option. So path is from A to B. You will get the path D, E, B, C, A, D, right? First D, E, A and D. Then come back to the vertex D, right? So here the weight is 3, here 2, here is 2, here is 4 and this is 5. Now the weight of the Hamiltonian circuit is 5 plus 4, 9, 9 plus 2, 11 plus 5, 16. Weight of Hamiltonian circuit is 16. Weight of Hamiltonian circuit is 16 here. Okay. So by using nearest neighborhood method, you can find out the weight of Hamiltonian circuit starting with vertex D as well as starting with vertex A here. Yeah, I hope you are getting clearly understand how to find out the Hamiltonian circuit with the help of nearest neighborhood method. Okay, now the next point, the same way you can find out the other examples also for the nearest neighborhood method. Okay, now we'll see the next point is here planar graph. Okay, planar graph. Next concept is planar graph. What do you mean by planar graph? A graph is said to be a planar graph. A graph a graph is said to be a planar graph. A graph is said to be a planar graph if it can be drawn, if it can be drawn on a plane in a such a way that no edges cross one another. No edges cross one another. Okay. Except at common vertices. Except at common vertices. Okay. Except at common vertices. So this is our planar graph. Okay. This planar. Now, if you draw this vertex on this same graph like this is also a planar. This is also a planar. But if you draw like this is not planar. Yes, it is planar. It is planar. This is not planar because these two edges are cross each other. So whenever these two edges are cross each other, that will not be a graph. But yes, this graph can be converted into planar graph like this. And these two edges you can draw like this. So this is a planar graph. Clear? I hope it is clear to you what you mean by planar graph and how it is converted into planar graph. Okay. For example, we can say, take here. So can you draw this as a planar graph? Suppose this is. Is this planar graph? Is this planar graph? So we can say. Actually, it is not a planar graph, but we can convert it into a planar graph. Okay. So this edge we can draw like this. Clear? Now, very important theorem, that is region. You mean by region? A planar representation of a graph divides the planes into regions, also known as a region is characterized by set of edges coming from the boundary. Okay, the unbounded region is known as exterior region. Suppose this is your graph. Okay, now this is your region 1, this is your region 2, and all the whole unbounded region is called as your region 3. Okay, so regions, the here a planar graph, planar representation of a graph divides the plane into regions. So these are the three regions for this plane, right? And the unbounded region is known, this is unbounded region, that unbounded region is also called as a region. Okay, now theorem on a regions, that is Euler polyhedra formula. Euler polyhedra formula. You can say that here, for any connected planar graph, for any connected planar graph, V minus E plus R is equal to 2. For any connected planar graph, V minus E plus R is equal to 2. V is the set of vertices, number of vertices, E is the number of edges, and R is the number of region. Okay? So for if you take two vertices, now see here, if you take the three vertices, graph on three vertices, 1, 2, suppose this is A, B, C. This is a graph on three vertices, right? So number of vertices are 3. V is equal to 3. Edges is equal to 3. Okay, regions here for bounded region and unbounded region are 2. You can cross verify with the polyhedra formula, Euler's polyhedra formula. 3 minus 3 plus 2 is equal to 2. Yes, it's verified. So by Euler's polyhedra formula, for any connected planar graph, V minus E plus R is equal to 2. The number of vertices minus number of edges plus number of regions is equal to always 2. Okay, so we can prove this by using the induction hypothesis, mathematical induction, as we have seen earlier. So how to prove that for any edge 1, region 1 and vertex 2. So you can calculate. Okay, so the most important corollary for this planar graph is if G is equal to vertex set V and edge set E is a simple connected planar graph, then E is less than or equal to 3V minus 6, where E is the total number of edges, where E is total number of edges and V is total number of vertices. And V is total number of vertices in the graph G. The graph, okay. So this is known as a K5. So complete graph on 5 vertices is a planar graph. Is non-planar graph. Complete graph on 5 vertices is a non-planar graph. Okay. Now, you can see that. Draw the, for example, draw a planar representation. Draw a planar representation of each graphs for the following. Each graphs for the following. Okay. Now suppose first graph. The graph is given like this. A, B, F. Right. Now draw the planar graph for this. So you can draw the planar graph. If I draw like this, A, means we have to preserve the relationship of this graph same. So A to E, A, C, D, B, F. So A to E is H, so like this. A to D is H, we can write this. To F, yes, F. To E, to E, to D, and B to F. Okay. A to C, and F to D. This is a planar graph for the given graph. One more graph is given. Second one. Okay. Here is A, B, C, D, E, F. So try to draw this graph as a planar graph. It means no cross edges are there. No cross edges are there. So we can draw this graph as a planar graph. Now see here. There are 6 vertices. Okay, all the edges are covered. Now if I draw the C to E like A, B, D, F. Now B to F. Can I draw this edge like this? B to F? Yes. B to D like this, D to E like here planar. Okay, so you can any graph you can convert it into planar graph by using this. If you can't convert it into like this without planar graph, it means there is no cross edges. Okay, if you can't convert it into this, then definitely that will be a non-planar graph. As I told you, the K5 complete graph on 5 vertices, it is a non-planar graph. We can say K5 is non-planar graph. Okay, we cannot adjust that. K5 it means complete graph on 5 vertices. It means degree of every vertex is n minus 1. Right? This is K5. The degree of every vertex is 4. Is your K5. So can we draw the graph without crossing the edges? No edge means a crossed edge. We can draw like this. Suppose I draw this edge like this. A, B, C, D and E. A, B, D and E. Can you draw this? So B to D edge. No. Can a B to E. E to D. These two edges. So I can draw this edge like this. A to D is edge like this. Right. A to B is over. A to E is over. A to C. Yes, I can draw like this. A to C. The degree of this vertex A is 4. Vertex B is 4. 1, 2, 3, 4. Vertex C is 4. But vertex C and E. This edge we cannot draw like this. If you go by like this, then this here will be cross. Okay. So two edges are cross. Okay. So this is a non-planar graph. So definitely, if you go like from C to E here, we cannot draw like this where the no two edges are crosses. So therefore K5 is a non-planar graph. I hope you are getting it clearly what you mean by planar graph, non-planar graph and Euler's polyhedra formula depending upon the regions. So it is covered. I think your total graph theory is covered in this. Okay. Total graph theory is covered in this. Only one topic is remaining, subtopic, that is trees. That tree part we will cover up in the next lecture. In that we will see the definition of tree, then properties of trees, bounded trees, rooted trees and everything. And also how to draw the complete bipartite tree, then rooted tree, binary search tree. Okay, by using the algorithm, it is post-order traversal, pre-order traversal and Huffman coding. That part we will cover up in the next lecture, and after that the minimum spanning tree, and that part will be covered in the next lecture. So please watching, and if you are liking my videos, please do like, share and subscribe. Please do like, share and subscribe. Thank you so much. I will be here tomorrow at the same time with the new topic, that is trees.